Hi, I'm Alan Puckett, and I'm going to be presenting and talking a little bit about Project 1 in graph analysis. So, the assignment was to go to the Doodle Connect, the game on the internet, and go through the first 16 challenges or puzzles they give you and find a path all the way through, which is actually a great way to learn this. I found that it was pretty interactive and I had words to describe it that I guess I didn't before after learning this class. So, um, kudos to Doodle Connect for coming up with a game like this and for us using it in a project. So let's go ahead and get started. So I just went ahead and chose graph 1 in the game to be the first graph to talk about. It's very simple. It has a lot of points that make it easy to talk about and really reference things. So it's just a simple four vertex graph. We'll move forward. So the degree of the graph obviously is a 2, 2, 2, and 2, and that's because all four of the vertices are connected by two edges. The adjacency matrix is as follows. Um, yeah, again, this is a very easy graph. It's nothing too crazy. A good Eulerian circuit would just be from 1 to 2 to 3 to 4 back to 1. In summary, this is definitely a Hamiltonian graph with the Hamiltonian cycle being 1, 2, 3, 4, and 1. Now this graph does have an edge connectivity of 2, and what that means is that if we were to erase two edges, we would end up with an isolated vertex. But there is possible to get the cut set where it would only delete the one, or only not isolate a point, but would still cut out an edge, and that would be if we were to cut out something like, let's say, 3, 4. So there are 3 4s cut out, and there's nothing isolated. Okay. Okay, so graph 8. This graph was a little bit more complex than the previous. It kind of stood out to me. It seems like something that I could have, that my imagination and creativity could have brought forth. So I chose this graph. It's a good little look at it. Again, a 7 vertex graph. And we'll dive right in now. Okay, so the degree sequence would be 2, 4, 3, 2, 3, 4, 2. And again, you get that from counting the edges connected to each vertex. The adjacency matrix is as follows. Yeah, so pretty much very easy to follow. And if we wanted to, we could make a Eulerian trail such that 3 to 4 to 5 to 6, 7 to 2 to 6 to 1 to 2 to 3 and to 5. And that's actually how I solved the puzzle. And that's it is a Eulerian trail because I didn't use a single edge twice. So I just continued with one, like I mentioned in one of my forum posts. A good way to think about it is if you just start at one vertex and you begin drawing the graph without picking your pen up or repeating a line. So I think that's a great way to think about it. This is definitely not a Hamiltonian graph because there are odd degrees in the sequence. So vertex 3 and vertex 5 both have 3, and we know that they're supposed to be even if it's going to be, well, one of the things would be a Hamiltonian graph to be even. Also, you're not supposed to touch this at a vertex twice. Much like the Eulerian, you can only use the edge once. Well, in a Hamiltonian, you can only use a vertex once in a path, and you would definitely hit a few of these vertexes twice. So the edge connectivity, again, with this is 2, and you'll see that vertex 4 has 2 edges, in which case, if you were to erase or have a cut set of those 2 edges of 4 to 5 and 3 to 4, then 4 would be isolated. So at most you could have a cut set of 1, which would be the cut set of 3, 4, and you would have an unisolated point 4, but still have a cut set there. And then again, if you were to actually have the cut set 4, 5 as well, that would be your isolated vertex 4. Okay, moving forward. The third graph I chose is graph 10 from the game. Again, it's a 7 vertex graph. This is just a good view of it. So we'll go ahead and move forward. Again, the degree sequence for this would be 2, 3, 2, 3, 4, 2, 4. And the adjacency matrix is as follows. Okay, so the Eulerian trail now that we can mention would be from 4 to 7 to 5 to 6 to 7 to 1 to 2 to 4 to 5 to 3 and to 2. So again, that is how I solved the puzzle. Actually, I just started at 4 actually and moved my way forward. And that seems to be one of the best ways I think to do it. This is definitely not a Hamiltonian graph again because there are odd degree sequences. So we know that we will have to hit a vertex twice in order to get some of these edges. And also, this is another edge connectivity of 2 because if we have a cut set, like I mentioned before, we'll end up isolating 6 because that's the most. And here you'll see there is a possibility to have a cut set without isolation, and that would be 6 and 7. And then to actually isolate it with the 2 edges would be that. Our final graph, graph 14, it is a 10 vertex graph, which is the biggest and most complex yet. This one's actually pretty interesting. I find the shape to be somewhat pleasing. The degree of connectivity would be 2, 3, 2, 4, 4, 2, 3, 2, 4, 4. And it's really interesting. It's repeating itself, so you can tell by looking at the graph that it's actually mirrored halfway in the middle from the left and to the right. So it's very simple. It all makes sense. You can kind of see it just from the numbers that it would look like this, or something like this anyways. So the adjacency matrix, this one will take a few seconds because it is a 10 by 10 matrix. Okay, so our Eulerian path, the one that I used to actually solve this, ends up being on the screen here, 6 to 5 to 4 to 3 to 2 to 10, 5 to 9 to 4 to 10 to 8 to 7 to 9 to 1 to 2. Now, one of the things again that you look at that path, and you possibly could make a Hamiltonian graph or a path out of here, but not the way that it's drawn, not the path that I've taken either to solve the puzzle. So again, this is definitely not Hamiltonian graph. And again, there are odd degree sequences. And one more time, this is an edge connectivity of 2. I think all of the actual graphs in the game might be an edge connectivity 2. I looked at quite a few of them. I didn't do this for every single graph, but I chose quite a few. So this is I believe that this is the case for all of them. But there is a cut set, of course. If there's edge connectivity 2, then it's possible to get a cut set without isolating a point, and that would be something like 5 to 6. A cut set of 5 to 6. That would be easy cut set. And if we wanted to isolate 6, then that's what it would look like. All right, so a couple things that helped me create this little presentation here today. The textbook obviously is a huge help. I find the textbook actually one of the best that I can read from and find information in, especially with the work that we have in the class. It's extremely relative, and then obviously Doodle Connect as well. So thank you. Hope you enjoyed. I'll see you soon.